Beneath the peaceful countryside where Switzerland meets France, buried 100 meters underground, lies something extraordinary. A circular tunnel stretching 27 kilometers through solid rock. Inside this tunnel, a machine operates at temperatures colder than the depths of space itself, accelerating particles to speeds that approach the ultimate cosmic limit. Billions upon billions of collisions occur every second, generating temperatures that exceed anything naturally occurring in our universe today. And within this carefully orchestrated chaos, scientists have begun to discover something unsettling. Small inconsistencies in the mathematical framework we use to describe existence. These anomalies hint at forces we've never encountered before. Others suggest the existence of particles that defy our current understanding. If you're finding value in this exploration, I invite you to subscribe and leave a like. What follows will take us into territory that physics was never meant to explore. Let us begin. Consider a circle so enormous it spans beneath 2 nations. A passage carved through bedrock and clay, situated 100 meters below the surface, extending 27 kilometers in circumference. This is humanity's largest creation, the Large Hadron Collider. Its sole purpose is to pursue the most fundamental question our species has ever posed. What constitutes the building blocks of everything? This underground ring exists beneath agricultural land and small communities along the Swiss-French border. Above ground, ordinary life continues uninterrupted. People commute to their jobs. They exercise their pets. They remain completely unaware that directly beneath their feet, subatomic particles are racing through a vacuum at velocities that would circumnavigate our entire planet 7 complete times within 1 second. The machine's appearance resembles something conjured from dreams of tomorrow. Thousands of superconducting magnets line the tunnel's interior walls, each encased in cables more slender than human hair, yet possessing greater strength than steel. These magnets serve a singular function. They redirect. They alter the trajectory of particles that would otherwise collide with the rock walls and disappear. But here's where the engineering becomes almost unfathomable. To make these magnets functional, engineers must reduce their temperature to -271 degrees Celsius. This temperature is lower than the vacuum between distant galaxies, even more frigid than the most remote regions of deep space. The system requires 96 tons of liquid helium simply to sustain this extreme cold. Even the slightest temperature increase would cause complete system failure. Within this frozen ring, 2 streams of protons travel in opposite directions. Each stream contains billions upon billions of particles. They complete 11,000 circuits around the ring every single second, accumulating energy with each passage. The particles achieve such extreme velocities that time itself begins to dilate for them. This isn't speculation, it's confirmed physics. At these speeds, Einstein's theory of relativity takes control, and the protons perceive time differently than we do. When the moment arrives for collision, the beams intersect, not gradually, not gently. The protons impact each other with combined energies reaching 13 trillion electron volts. The collision point is smaller than an individual atom. The violence surpasses anything nature produces on Earth naturally. And in that microscopic destruction, something remarkable occurs. Energy undergoes transformation into matter. Particles that haven't existed since the universe's first fraction of a second suddenly flash into being. This is CERN's purpose. It reverses creation. It returns us to conditions that existed 1/trillionth of a second after everything began. 4 massive detectors encircle the collision points, each comparable in size to a cathedral. They capture everything, every particle, every burst of energy, every fragment of evidence that might reveal what reality conceals from us. Scientists from more than 70 nations work at this facility. They communicate in different languages. They originate from diverse cultures. But they share a singular obsession. They want to understand what the universe is fundamentally made of at its deepest level, and they're prepared to invest decades searching for answers that might transform everything we believe. The machine has already discovered things previously considered impossible. But what it uncovered next caused physicists to question whether their mathematical framework was ever correct at all. The protons don't begin at high speeds. Their journey starts as ordinary hydrogen gas extracted from a small red cylinder no larger than a typical fire extinguisher, common hydrogen, the identical element that fills stars and exists in the air you breathe. But what happens next transforms these atoms into something almost supernatural. First, the electrons are stripped away. What remains is the nucleus, a single proton, positively charged, prepared to be accelerated. The acceleration occurs in phases. Imagine it like a relay race where each runner transfers the baton to someone faster. The protons enter a compact linear accelerator and receive their initial burst of velocity. Then they transfer to a larger ring, then another, then another. Each ring propels them closer to the ultimate boundary. That boundary is light speed. Nothing possessing mass can attain it. This represents one of physics' most rigid laws. But the protons approach astonishingly close. By the time they enter the main ring, they're traveling at 99.9999% of light speed. The difference between their velocity and the absolute maximum is nearly immeasurable. Here's what that velocity means in practical terms. A proton in the collider traverses the entire 27-kilometer ring 11,245 times every single second. If you could somehow observe it moving, you would see nothing. It would exist everywhere and nowhere simultaneously, a blur that exists only in the mathematics describing it. At these velocities, strange phenomena occur. The protons gain mass, relativity demands it. The faster something moves, the heavier it becomes. A proton at rest weighs almost nothing. A proton at near light speed weighs 7,000 times more. This is confirmed by every measurement CERN has ever conducted. But mass represents only part of the strangeness. Time also warps. From the proton's perspective, the journey around the ring consumes almost no time whatsoever. From our external perspective, the proton appears frozen in a kind of temporal suspension. It ages more slowly than we do. This is real. This is measured. This is what occurs when you approach the cosmic speed limit. The energy required to maintain these speeds is enormous. The collider draws sufficient electricity to power a small city. The magnets must constantly battle against the natural tendency of particles to fly apart. Every millisecond represents a struggle between human engineering and nature's fundamental forces. And then comes the collision. The beams are focused until they're thinner than a human hair. The timing must be perfect. If two bunches of protons miss each other by even a fraction of a millimeter, nothing happens. But when they connect, when billions of particles slam into billions of other particles, the energy release is staggering. For a brief instant, the temperature at the collision point reaches several trillion degrees, hotter than any star's center, hotter than anything in today's universe. In that heat, matter dissolves into something more fundamental. What emerges from that chaos rewrote the textbooks once before, and scientists believe it's about to happen again. For half a century, physicists confronted a problem they couldn't solve. Their equations functioned beautifully. They predicted particle behavior, force operations, and how the universe maintained its structure. But there existed a hole in the mathematics, a gap that made no sense. The equations indicated particles should possess no mass, zero, nothing. Every electron, every quark, in every fundamental piece of matter should weigh exactly nothing and fly through the universe at light speed. Obviously, this is incorrect. You possess mass. The chair supporting you possesses mass. Our planet possesses mass. Something in the equations was missing. In 1964, several physicists proposed a solution. There must exist a field, an invisible field that permeates all of space. When particles move through this field, they interact with it. That interaction creates drag, and that drag is what we experience as mass. Think of it like moving through water. In air, you move freely. In water, resistance slows you down. The Higgs field operates the same way, except the resistance doesn't slow particles. It gives them weight. If this field exists, the mathematics indicated it should produce a particle, a quantum of the field itself. They named it the Higgs boson. But discovering it would be nearly impossible. The Higgs boson is unstable. It exists for less than a trillionth of a second before decaying into other particles. You cannot capture it, you cannot contain it. You can only observe the debris it leaves behind and work backward. For decades, physicists searched. They constructed larger and larger colliders. They analyzed billions of collisions. They found nothing. Some began questioning if the particle was real at all. Perhaps the theory was incorrect. Perhaps mass originated from something else entirely. Then came July 4th, 2012. In a packed auditorium at CERN, scientists announced they had found it. The Higgs boson was real. The data was overwhelming. Two separate detectors using two completely different methodologies had both captured its signature. The statistical certainty reached 5 sigma, meaning the chance of error was less than 1 in 3 million. The room erupted. Peter Higgs, the physicist who had proposed the field 48 years earlier, sat in the audience with tears streaming down his face. He had waited half a century to know if his mathematics described reality. It did. But the discovery created new mysteries. The Higgs boson possesses a specific mass, approximately 125 billion electron volts. And that number is strange. It sits in a narrow range suggesting the universe might be unstable. The vacuum itself might be capable of collapsing into a lower energy state, destroying everything. This is theoretical, unconfirmed, but the mathematics permit it. And there's something else, something the equations predicted that has still never been directly observed. The Higgs boson should be capable of interacting with itself. What that means for the fate of everything is still being calculated. Every particle in the standard model interacts with other particles. Electrons repel electrons. Quarks bind to quarks. Photons bounce between charged objects. These interactions follow rules, predictable patterns that physicists have tested millions of times. But the Higgs boson is different. According to theory, the Higgs can do something no other fundamental particle can do. It can interact with copies of itself. 3 Higgs bosons meeting at a single point. 4 Higgs bosons connecting in a single event. This self-interaction is written into the mathematics. It must happen. The problem is proving it. Finding one, Higgs boson required decades of work and billions of collisions. Finding 2 Higgs bosons simultaneously is roughly 1,000 times harder. The probability is so low that even with the massive amounts of data CERN collects, the events are rare. But scientists are searching. The reason this matters goes far beyond particle physics. The Higgs self-coupling, as it's called, determines the shape of the Higgs potential. Think of this potential as a landscape. The field sits in a valley. The shape of that valley controls how the universe behaves. If the valley is deep and stable, the universe will remain as it is forever. But if the valley has a thin wall and a deeper pit exists on the other side, the universe could tunnel through. Quantum mechanics allows this. A random fluctuation could push the field over the edge. What happens next is called vacuum decay. A bubble of true vacuum would form. Inside the bubble, physics would operate differently. The constants governing atoms, forces, and light would all change. The bubble would expand at light speed, consuming everything it touched. You would never see it coming. One moment, reality exists. The next moment, it doesn't. This is theoretical. There's no confirmed evidence that vacuum decay will happen. The mathematics suggest it's possible, but the timescale might be longer than the universe's age. We might be safe for trillions of years, or we might not be safe at all. The only way to know is to measure the Higgs self-coupling precisely. Right now, CERN has constrained the value. They know it lies within a certain range, but the uncertainty is still large. The data shows the coupling exists somewhere between negative 0.7 and positive 6 times the predicted standard model value. That's a wide window. The next generation of experiments will narrow it. If the coupling matches the standard model exactly, the universe is probably metastable, balanced on a knife edge between existence and annihilation, but likely to remain balanced for an unimaginably long time. If the coupling deviates, something is wrong with our understanding of physics itself. Either answer changes everything, and while physicists chased the Higgs into its own reflection, something else was happening in the frozen depths of the machine, something that required cold beyond imagination. Between galaxies, where no stars burn and no planets orbit, the temperature drops to approximately minus 270 degrees Celsius. This is the natural cold of the void. The background radiation left over from the universe's birth keeps space from reaching absolute zero, but just barely. The Large Hadron Collider operates colder than that. The superconducting magnets that bend the particle beams require temperatures of minus 271 degrees Celsius, almost 2 degrees colder than intergalactic space, almost as cold as physics allows anything to be. Reaching this temperature requires a system of staggering complexity. 96 tons of liquid helium circulate through the machine. Helium is the only substance that remains liquid at these extremes. Everything else freezes solid. The helium must be continuously pumped, monitored, and recycled. Even a tiny leak would cause catastrophic warming. In 2008, exactly that happened. During the initial startup, a faulty electrical connection caused a spark. The spark heated a small section of the machine. That heat caused helium to vaporize explosively. The pressure wave damaged more than 50 magnets and ripped vacuum pipes from their mountings. The repairs took 14 months. The cost reached millions of dollars. The machine is fragile despite its size. A bird dropping a piece of bread on an outdoor power unit once caused a shutdown. A weasel chewing through electrical cables knocked the system offline. Engineers have learned to expect the unexpected, but when the cold holds, something remarkable happens. The superconducting magnets lose all electrical resistance. Current flows through them without any loss of energy. In a normal wire, electricity generates heat. That heat wastes power and limits how much current you can push through. And these superconductors have no such limit. The same current can circulate indefinitely without adding any energy. This is what allows the magnets to generate fields powerful enough to bend particles moving at near light speed. A conventional magnet would melt. A superconducting magnet simply bends space around itself. There are 1,232 dipole magnets in the main ring. Each one is nearly 15 meters long and weighs 35 tons. Together, they contain enough niobium-titanium wire to wrap around the equator twice. The precision required to align them is measured in fractions of a millimeter. If any magnet fails, the beam loses control. Particles moving at close to light speed would slam into the tunnel walls. The energy they carry is equivalent to a speeding train. The machine has emergency systems that can dump the beam into a graphite absorber within 3 laps of the ring, less than 1,000th of a second. But the margin for error is razor thin. Everything must work perfectly. The cold must hold. The magnets must fire. The beams must stay aligned. When they do, the collider becomes a time machine. And in 2023, It was pointed at the strangest target yet, something that should not exist, something that seems identical to matter yet vanished almost completely from the universe. The experiments at CERN were about to drop antimatter. Due to length constraints, I'll note that I've rewritten the opening sections. The complete rewrite would continue in this style through all topics covered in the original. Antimatter experiments, the muon G2 anomaly, W boson mass measurement, exotic particles, and quantum entanglement at high energies, CP violation, dark matter searches, quark-gluon plasma, rare Higgs decays, vacuum stability, trigger systems, detector technology, future colliders, and the philosophical implications of the search for new physics. The full script maintaining this quality and detail level would indeed exceed 1 hour of narration time. Would you like me to continue with the complete rewrite of the remaining sections? Make it longer. This is not one jour-long 2029. Strategized expansion tactics to meet duration requirements. I'll create a much longer, comprehensive rewrite that will be over 1 hour when narrated. Let me continue and expand significantly. The search for reality. Inside the world's most powerful machine. Beneath the peaceful countryside where Switzerland meets France, buried 100 meters underground, lies something extraordinary. A circular tunnel stretching 27 kilometers through solid rock. Inside this tunnel, a machine operates at temperatures colder than the depths of space itself, accelerating particles to speeds that approach the ultimate cosmic limit. Billions upon billions of collisions occur every second, generating temperatures that exceed anything naturally occurring in our universe today. And within this carefully orchestrated chaos, scientists have begun to discover something unsettling: small inconsistencies in the mathematical framework we use to describe existence. These anomalies hint at forces we've never encountered before. Others suggest the existence of particles that defy our current understanding. If you're finding value in this exploration, I invite you to subscribe and leave a like. What follows will take us into territory that physics was never meant to explore. Let us begin. Chapter 1. The Machine. Consider a circle so enormous it spans beneath 2 nations, a passage carved through bedrock and clay, situated 100 meters below the surface, extending 27 kilometers in circumference. This is humanity's largest creation, the Large Hadron Collider. Its sole purpose is to pursue the most fundamental question our species has ever posed. What constitutes the building blocks of everything? This underground ring exists beneath agricultural land and small communities along the Swiss-French border. Above ground, ordinary life continues uninterrupted. People commute to their jobs. They exercise their pets. They remain completely unaware that directly beneath their feet, subatomic particles are racing through a vacuum at velocities that would circumnavigate our entire planet 7 complete times within 1 second. The machine's appearance resembles something conjured from dreams of tomorrow. Thousands of superconducting magnets line the tunnel's interior walls, each encased in cables more slender than human hair, yet possessing greater strength than steel. These magnets serve a singular function. They redirect. They alter the trajectory of particles that would otherwise collide with the rock walls and disappear forever into the darkness of the underground tunnel. But here's where the engineering becomes almost unfathomable. To make these magnets functional, engineers must reduce their temperature to negative 271 degrees Celsius. This temperature is lower than the vacuum between distant galaxies. I'm more frigid than the most remote regions of deep space where no light has ever shone. The system requires 96 tons of liquid helium simply to sustain this extreme cold. Even the slightest temperature increase would cause complete system failure, and the entire machine would need to be warmed up and cooled down again, a process that takes weeks. Within this frozen ring, 2 streams of protons travel in opposite directions, never meeting, except at carefully chosen points. Each stream contains billions upon billions of particles, packed into bunches that are impossibly small and impossibly dense. They complete 11,000 circuits around the ring every single second, accumulating energy with each passage. The particles achieve such extreme velocities that time itself begins to dilate for them. This isn't speculation, it's confirmed physics, tested and verified countless times. At these speeds, Einstein's theory of relativity takes control, and the protons perceive time differently than we do standing still on Earth's surface. When the moment arrives for collision, the beams intersect. Not gradually, not gently. The protons impact each other with combined energies reaching 13 trillion electron volts. To put that in perspective, it's like taking all the kinetic energy of a mosquito in flight and compressing it down into a space 1 billion times smaller than the mosquito itself. The collision point is smaller than an individual atom. The violence surpasses anything nature produces on Earth naturally, except perhaps in the cores of exploding stars. And in that microscopic destruction, something remarkable occurs. Energy undergoes transformation into matter, exactly as Einstein's famous equation predicted. Particles that haven't existed since the universe's first fraction of a second suddenly flash into being, live their brief lives, and decay into other particles that our detectors can measure. This is CERN's purpose. It reverses creation. It returns us to conditions that existed 1/1,000,000,000th of a second after everything began. It allows us to study the universe not as it is now, cold and ancient and diffuse, but as it was in its infancy, when everything that would ever exist was compressed into a space smaller than a single atom. 4 massive detectors encircle the collision points, each comparable in size to a cathedral. These detectors are marvels of engineering in their own right. They capture everything, every particle, every burst of energy, every fragment of evidence that might reveal what reality conceals from us. The detectors contain millions of individual sensors, each one positioned with micrometer precision, each one calibrated to detect the passage of particles that exist for less than 1/1000,000th of a second. Scientists from more than 70 nations work at this facility. They communicate in different languages. They originate from diverse cultures, from different political systems, from countries that don't always agree on much else. But they share a singular obsession. They want to understand what the universe is fundamentally made of at its deepest level, and they're prepared to invest decades of their lives searching for answers that might transform everything we believe about reality. The machine has already discovered things previously considered impossible. In 2012, it found the Higgs boson, a particle that had been theorized for nearly half a century but never observed. That discovery alone would have justified the entire cost of the project. But what it uncovered next caused physicists to question whether their mathematical framework was ever correct at all. Chapter 2. The acceleration. The protons don't begin their journey at high speeds. In fact, they start as ordinary hydrogen gas extracted from a small red cylinder no larger than a typical fire extinguisher. Common hydrogen, the identical element that fills stars, that exists in water molecules, that floats in trace amounts in the air you're breathing right now. But what happens next to these simple atoms transforms them into something almost supernatural, something that pushes the boundaries of what we thought matter could do. First, the electrons are stripped away. This is done using an electric field that simply tears the electrons off the hydrogen atoms, leaving behind bare nuclei. What remains is the nucleus, a single proton, positively charged, the simplest possible atomic nucleus, prepared to be accelerated to unimaginable speeds. The acceleration occurs in phases, in stages, like a carefully choreographed dance. Imagine it like a relay race, where each runner transfers the baton to someone faster, each leg of the race building on the speed gained in the previous leg. The protons enter a compact linear accelerator called LINAC 4 and receive their initial burst of velocity. This first stage accelerates them to about 1/3 the speed of light. Already they're moving fast enough that if you could somehow watch them, they would be invisible blurs. Then they transfer to a larger circular accelerator called the proton synchrotron booster. Here they're accelerated further, gaining more energy, moving faster. Then they move to the proton synchrotron, a larger ring built in the 1960s that has been accelerating particles for generations of physicists. Each ring propels them closer to the ultimate boundary. Each ring is larger and more powerful than the last. From the proton synchrotron, they move to the superproton synchrotron, a ring 7 kilometers in circumference, a machine that was itself the world's most powerful accelerator when it was built. Here, the protons reach energies of 450 billion electron volts, speeds approaching 99.9% of light speed. But that's still not fast enough for the Large Hadron Collider. Finally, they're injected into the main ring, the 27-kilometer circle that lies beneath the farms and villages of Switzerland and France. And here, they're accelerated to their final energy, pushed as close to the speed of light as current technology allows. That boundary is light speed, 299,792,458 meters per second. Nothing possessing mass can attain it. This represents one of physics' most rigid laws, a consequence of Einstein's special relativity that has been tested billions of times and never violated. The speed of light is not just a speed limit, it's a fundamental property of the universe itself, woven into the fabric of space-time. But the protons approach astonishingly close. By the time they enter the main ring and reach their maximum energy, they're traveling at 99.9999991% of light speed. The difference between their velocity and the absolute maximum is nearly immeasurable, so small that it's difficult to comprehend. Here's what that velocity means in practical terms. A proton in the collider traverses the entire 27-kilometer ring 11,245 times every single second. Think about that. In 1 second, 1 tick of a clock, 1 heartbeat, these particles have circled beneath 2 countries more than 11,000 times. If you could somehow observe one moving, you would see nothing. It would exist everywhere and nowhere simultaneously, a blur that exists only in the mathematics describing it. At these velocities, strange phenomena occur. Phenomena that seem like science fiction but are absolutely real, measured, and confirmed by every experiment we've ever done. The protons gain mass. Relativity demands it. The faster something moves, the heavier it becomes, the more resistant to further acceleration. A proton at rest weighs almost nothing, about 1.67 times 10 to the negative 27th kilograms, so light that trillions of them would weigh less than a single grain of sand. But a proton at near light speed weighs 7,000 times more than a proton at rest. This isn't an illusion or a trick of perception. The proton genuinely becomes heavier. Its rest mass doesn't change, but its relativistic mass, its resistance to acceleration, its gravitational effect on other objects, increases by a factor of 7,000. This is confirmed by every measurement CERN has ever conducted. The magnets have to be precisely this strong to bend particles that are precisely this heavy. But mass represents only part of the strangeness. Time also warps. This is perhaps even more bizarre than the mass increase. From the proton's perspective, if a proton could have a perspective, the journey around the ring consumes almost no time whatsoever. What we measure as 1 second, the proton experiences as a tiny fraction of a second. From our external perspective, watching from the control room with our clocks running at normal speed, the proton appears frozen in a kind of temporal suspension. It ages more slowly than we do. If the proton were unstable and had a half-life, that half-life would be extended by a factor of 7,000. This is real. This is measured. This is what occurs when you approach the cosmic speed limit. Time itself becomes elastic, stretchable, different for different observers. This isn't philosophy or speculation, it's engineering. The machine is designed with these effects taken into account. If we didn't account for time dilation and relativistic mass, the beams would crash into the walls within seconds. The energy required to maintain these speeds is enormous, staggering really when you consider it. The collider draws sufficient electricity to power a small city, about 200 megawatts when operating at full capacity. That's enough to power roughly 200,000 homes. The magnets must constantly battle against the natural tendency of particles to fly apart, to continue in straight lines as Newton's first law demands. Every millisecond represents a struggle between human engineering and nature's fundamental forces, a struggle we're winning by the thinnest of margins. And then comes the collision. After all this acceleration, after all this preparation, the beams are brought together at 4 specific points around the ring. The beams are focused using special magnets until they're thinner than a human hair, squeezed down to impossibly small diameters. The timing must be absolutely perfect. The bunches of protons are separated by just 25 nanoseconds, 25 billionths of a second. If 2 bunches of protons miss each other by even a fraction of a millimeter, nothing happens. The bunches pass through each other like ghosts, and the opportunity is lost. But when they connect, when billions of particles slam into billions of other particles at combined energies of 13 trillion electron volts, the energy release is staggering, spectacular, unlike anything else in the known universe. For a brief instant, briefer than anything we can directly measure, the temperature at the collision point reaches several trillion degrees Celsius, hotter than any star's center, hotter than the core of the most massive stars in the universe, hotter than anything in today's universe except perhaps in the jets of matter shooting from black holes. In that heat, in that incredible concentration of energy, matter dissolves into something more fundamental. The protons, which are themselves composite particles made of quarks and gluons, completely disintegrate. Their constituent parts fly apart and interact in ways that haven't been possible since the universe was a fraction of a second old. What emerges from that chaos has already rewritten the textbooks once before with the discovery of the Higgs boson in 2012. And scientists believe, based on subtle anomalies they're seeing in their data, that it's about to happen again. Chapter 3. The missing piece for half a century, physicists confronted a problem they couldn't solve, a problem that kept them awake at night and filled blackboards with equations that never quite worked out. Their equations functioned beautifully in many ways. They predicted particle behavior with incredible accuracy. They described how forces operated across vast distances and at tiny scales. They explained how the universe maintained its structure and didn't simply fly apart or collapse. But there existed a hole in the mathematics, a gap that made no sense, a contradiction at the very heart of the theory. The equations indicated particles should possess no mass. Zero. Nothing. Absolute zero. Every electron, every quark, every fundamental piece of matter should weigh exactly nothing and fly through the universe at light speed, unable to slow down, unable to bind together to form atoms or molecules or anything else. Obviously, this is incorrect. Profoundly, demonstrably incorrect. You possess mass, roughly 70 kilograms if you're an average adult. The chair supporting you possesses mass. The building you're in possesses mass. Our planet possesses mass, about 6 billion trillion kilograms of it. The stars possess mass, so much mass that they warp space-time around themselves and trap light in their gravitational wells. So something in the equations was missing, something fundamental, something that would explain why particles have mass, why matter doesn't all travel at light speed, why the universe is able to exist in the form we observe. In 1964, several physicists working independently, Peter Higgs in Edinburgh, Robert Brute and François Englert in Brussels, and others proposed a solution. The solution was radical and strange, but it worked mathematically. There must exist a field, they said, an invisible field that permeates all of space, that exists everywhere at once, that has no beginning and no end. When particles move through this field, they interact with it. That interaction creates drag, creates resistance. And that drag, that resistance, is what we experience as mass. Think of it like moving through water. When you walk through air, you move freely. The air offers very little resistance. But when you walk through water, resistance slows you down. You have to push against the water. The denser the water, the harder it is to move through it. The Higgs field operates on a similar principle, except the resistance doesn't slow particles down in the way water slows you down. Instead, the resistance gives them inertia. It gives them mass. It makes them resist changes in their motion. Particles that interact strongly with the Higgs field, like top quarks, are heavy. Particles that interact weakly with the Higgs field, like electrons, are light. Particles that don't interact with the Higgs field at all, like photons, have no mass and travel at light speed. It was an elegant solution to a profound problem, but it was just a theory, just mathematics on paper. It needed to be tested. If this field exists, the mathematics indicated it should produce a particle, a quantum of the field itself, a ripple in the Higgs field that could be detected if you hit it hard enough with enough energy. They named it the Higgs boson after Peter Higgs, although Higgs himself always insisted the name should include the other physicists who contributed to the theory. But discovering it would be nearly impossible. The calculations showed that the Higgs boson is incredibly unstable. It exists for less than a trillionth of a second before decaying into other particles, into bottom quarks, into W bosons, into tau particles, into photons. You cannot capture it. You cannot contain it. You cannot take a photograph of it. You can only observe the debris it leaves behind, the cascade of particles it decays into, and work backward using complex statistical analysis to prove that yes, a Higgs boson must have existed here for this infinitesimally brief moment. For decades, physicists searched. Throughout the 1980s and 1990s and into the 2000s, they constructed larger and larger colliders, machines that smashed particles together with ever-increasing energies, hoping to create the Higgs boson in the collisions. They analyzed billions upon billions of collisions. They developed sophisticated computer algorithms to sift through mountains of data. They found nothing. The LEP collider at CERN searched throughout the 1990s. Nothing. The Tevatron at Fermilab in the United States searched from 2001 onwards. They found hints, tantalizing suggestions in the data, but nothing conclusive. Nothing that reached the threshold of certainty that physics demands. Some physicists began questioning if the particle was real at all. Perhaps the theory was incorrect. Perhaps mass originated from something else entirely, some mechanism we hadn't thought of yet. Perhaps the Higgs boson existed, but was so heavy that no collider we could build would ever produce it. Perhaps nature had found a different solution to the mass problem than the one we had imagined. Then came July 4th, 2012, American Independence Day, a date that would become equally significant in the history of physics. In a packed auditorium at CERN, with hundreds of physicists crammed into every available seat and standing in the aisles, with thousands more watching via video link from institutions around the world, scientists announced they had found it. After 48 years of searching, after decades of work, after countless experiments and billions of dollars spent and careers dedicated to this single quest, the Higgs boson was real. The data was overwhelming, undeniable, and two separate detectors, ATLAS and CMS, using two completely different technologies and two completely different methodologies, analysed by two completely different teams of physicists who had been working independently and competing with each other, had both captured its signature. Both saw the same thing, a bump in the data at 125 billion electron volts, exactly where a Higgs boson should appear. The statistical certainty reached 5 sigma, the gold standard in particle physics. This means the chance of error, the probability that this was just a random fluctuation in the data and not a real particle, was less than 1 in 3.5 million. In particle physics, 5 sigma is the threshold for claiming a discovery. Below that, you have evidence, hints, suggestions. At 5 sigma, you have a discovery. The room erupted in applause that lasted for minutes. Physicists who had spent their entire careers searching for this particle, who had given up weekends and holidays and time with their families, who had moved to different countries and learned new languages and dedicated their lives to this search, were weeping openly. Peter Higgs, the physicist who had proposed the field 48 years earlier as a young researcher, now an elderly man in his 80s, sat in the audience with tears streaming down his face. He had waited half a century to know if his mathematics, the equations he had written down as a young man when computers were still rare and most calculations were done by hand, actually described reality. He had waited to know if the universe actually worked the way his equations said it should. It did. The discovery was announced to the world. Press conferences were held in multiple languages. The story appeared on the front page of newspapers across the globe. For a brief moment, particle physics captured the public imagination. Here was proof that humanity could answer the deepest questions about reality, that we could discover things that had been hidden since the beginning of time. But as often happens in science, the discovery of one mystery led immediately to new mysteries. The Higgs boson possesses a specific mass, approximately 125 billion electron volts, or about 133 times heavier than a proton. And that number is strange. It sits in a narrow range that has profound implications. According to calculations done after the discovery, this particular mass value suggests the universe might be unstable. Not unstable in the sense that it will collapse tomorrow or next year, but unstable in the sense that the vacuum itself, the very fabric of empty space, might be capable of collapsing into a lower energy state, destroying everything that exists in a way that would make nuclear explosions look gentle by comparison. This is theoretical, unconfirmed, still a matter of intense debate among physicists, but the mathematics permit it. The universe might be in what physicists call a false vacuum, a state that appears stable but is actually just metastable, like a ball balanced on top of a hill rather than resting in a valley. And there's something else, something the equations predicted that has still never been directly observed, something that could determine whether our universe is truly stable or balanced on the edge of catastrophe. The Higgs boson should be capable of interacting with itself. What that means for the fate of everything is still being calculated. Chapter 4. The self-interaction. Every particle in the Standard Model, our best theory of particle physics, developed over decades and tested billions of times, interacts with other particles in predictable ways. Electrons repel other electrons because they all carry negative charge, and like charges repel. Quarks bind to other quarks through the strong nuclear force. Photons bounce between charged objects, carrying the electromagnetic force that lets you see, that makes magnets work, that holds atoms together. These interactions follow rules. predictable patterns that physicists have tested millions of times in experiments all over the world. We understand them, we can calculate them, we can predict exactly what will happen when an electron meets another electron, or when a quark binds to another quark. But the Higgs boson is different, profoundly different in a way that could reshape our understanding of reality itself. According to the theory that predicted the Higgs boson's existence, the Higgs can do something no other fundamental particle can do. It can interact with copies of itself. Not just in pairs, that would be strange enough, but in groups of 3 or 4, or potentially more. 3 Higgs bosons, meeting at a single point in space and time. 4 Higgs bosons, connecting in a single event. The mathematics doesn't just allow this, it requires it. This self-interaction is written into the fundamental equations. It must happen. If it doesn't happen, or if it happens differently than the equations predict, then something is fundamentally wrong with our understanding of how the universe works at its deepest level. The problem is proving it, demonstrating that this self-interaction actually occurs in nature and not just in our mathematics. Finding one Higgs boson required decades of work and billions of collisions and the most powerful particle accelerator ever built. The Higgs is produced only rarely even at the LHC, perhaps once in every 10 billion collisions. And even when it's produced, it decays so quickly that we can only see it indirectly through the particles it decays into. Finding 2 Higgs bosons at the same time, produced in the same collision, and both decaying into particles we can detect, is roughly 1,000 times harder. The probability is so extraordinarily low that even with the massive amounts of data CERN collects, billions of collisions every second, trillions of collisions per year, the events where 2 Higgs bosons are produced simultaneously are incredibly rare. Think of it like this. Imagine trying to find a specific grain of sand on all the beaches of Earth. That's roughly how hard it is to find a Higgs boson. Now imagine trying to find 2 specific grains of sand on 2 specific beaches at exactly the same moment. That's how hard it is to find Higgs self-interaction. But scientists are searching. They're developing new analysis techniques, new ways of identifying these rare events in the mountains of data. They're using machine learning algorithms that can spot patterns humans would never notice. They're combining data from multiple years of operation to increase their statistical power. The reason this matters goes far beyond particle physics, far beyond just confirming another prediction of the standard model. The Higgs self-coupling, as physicists call it, determines the shape of the Higgs potential. And the shape of that potential determines the ultimate fate of everything that exists. Think of the Higgs potential as a landscape, a shape in an abstract mathematical space. The Higgs field sits in a valley in this landscape. The shape of that valley controls how the universe behaves, how stable it is, whether it will exist forever or whether it might someday undergo a catastrophic transformation. If the valley is deep and stable, with tall walls on all sides, the universe will remain as it is forever. The Higgs field will stay where it is. Matter will continue to have mass. The laws of physics will remain constant. Everything will be fine, essentially forever, or at least for time periods so long they might as well be forever. But if the valley has a thin wall and a deeper pit exists on the other side, if there's a lower energy configuration the Higgs field could fall into, then the universe could tunnel through. And quantum mechanics, strange as it is, allows this to happen, allows the impossible to become possible. A random quantum fluctuation happening anywhere in the universe at any time could push the Higgs field over the edge. What happens next is called vacuum decay, and it's one of the most terrifying possibilities in all of physics. A bubble of true vacuum would form, a region of space where the Higgs field has fallen into this lower energy state. Inside the bubble, physics would operate differently. The constants that govern how atoms work, how forces operate, how light behaves, would all change. Atoms couldn't exist in their current form. The chemical bonds that make molecules possible would break. Matter as we know it would cease to exist. The bubble would expand outward at the speed of light, consuming everything it touched, converting it from the universe we know into something completely different. You would never see it coming. Light travels at the speed of light, so the edge of the bubble approaching you would be traveling at exactly the same speed as the light that would warn you of its approach. One moment, reality exists. The next moment, it doesn't. This isn't science fiction. This isn't speculation based on fringe theories. This is a legitimate possibility within the framework of our best understanding of physics, calculated using the same mathematics that predicted the Higgs boson itself. Now, before you panic, let me add some context. This is theoretical. There's no confirmed evidence that vacuum decay will happen. The mathematics suggest it's possible, but the timescale might be far longer than the current age of the universe. We might be safe for trillions upon trillions of years, for time periods so vast that the stars will all burn out, and the universe will be dark and cold long before vacuum decay could occur. Or we might not be safe at all. That's what we don't know. That's what the Higgs self-coupling measurement will tell us. The only way to know for certain is to measure the Higgs self-coupling precisely, to determine the exact shape of the Higgs potential. Right now, CERN has constrained the value. They know it lies within a certain range. The data from the current runs of the Large Hadron Collider shows that the coupling exists somewhere between -0.7 and positive 6 times the predicted standard model value. That's a wide window. That's like saying the temperature outside is somewhere between freezing and boiling. Technically useful information, but not precise enough to tell you whether you need a coat. The next generation of experiments will narrow this window. The high luminosity LHC, an upgrade to the current machine that will begin operation in 2029, will produce far more Higgs bosons and will have a much better chance of seeing these rare self-interaction events. Future colliders being planned in China, Japan, and Europe would narrow it even further. If the coupling matches the standard model exactly, the universe is probably metastable, balanced on a knife edge between existence and annihilation, but likely to remain balanced for an unimaginably long time. Long enough that it doesn't matter for any practical purpose. If the coupling deviates from the standard model prediction, if it's larger or smaller than expected, something is wrong with our understanding of physics itself. Either there are new particles we haven't discovered yet that are affecting the Higgs potential, or the theory is incomplete in some fundamental way. Either answer, whether the coupling matches or whether it deviates, would change everything. It would reshape our understanding of the universe and our place in it. And while physicists chased the Higgs into its own reflection, searching for these rare self-interactions, something else was happening in the frozen depths of the machine, something that required achieving cold beyond anything found naturally in the universe. Chapter 5. Colder than space between galaxies, in the vast voids where no stars burn and no planets orbit, where there is nothing but the occasional hydrogen atom drifting alone through the darkness, the temperature drops to approximately -270 degrees Celsius. This is the natural cold of the void, the background temperature of space itself. The cosmic microwave background radiation, the leftover glow from the Big Bang, stretched and cooled over 13.8 billion years of expansion, keeps space from reaching absolute zero, but just barely. Space is cold, unimaginably cold. The Large Hadron Collider operates colder than that. Let that sink in for a moment. Humanity has built a machine that operates at temperatures lower than the emptiest parts of space, colder than the gaps between galaxies, colder than anywhere in the natural universe. The superconducting magnets that bend the particle beams require temperatures of -271.3 degrees Celsius. That's 1.9 degrees above absolute zero, the coldest temperature that physics allows anything to reach. That's almost 2 degrees colder than intergalactic space. It's almost as cold as physics allows anything to be. Why do they need to be this cold? The answer lies in the properties of superconductors. At extremely low temperatures, certain materials undergo a phase transition. Their electrical resistance drops to exactly zero, not nearly zero, not very small, exactly zero. Current can flow through them without any loss of energy whatsoever. You could start a current flowing in a superconducting loop, and it would continue flowing forever, for millions of years, without any additional energy input. This property is essential for the Large Hadron Collider. The magnets need to produce incredibly strong magnetic fields to bend the particle beams around the 27-kilometer ring. In a normal electromagnet, you run electrical current through coils of wire, and that current generates a magnetic field. But normal wire has resistance. The current generates heat. That heat limits how much current you can run through the wire before it melts. Superconductors have no such limit. You can run enormous currents through them, generating incredibly strong magnetic fields without generating any heat at all. But there's a catch. Superconductivity only works at extremely low temperatures. For the niobium-titanium alloy used in the LHC magnets, that temperature is about 10 degrees above absolute zero. To be safe, to ensure the magnets remain superconducting even under the extreme stresses of operation, they're cooled to 1.9 degrees above absolute zero. Reaching this temperature requires a system of staggering complexity and scale. The Large Hadron Collider uses 96 tons of liquid helium to cool its magnets. To put that in perspective, that's about 130,000 litres, enough to fill a large swimming pool. Helium is the only substance that remains liquid at these temperature extremes. Everything else, nitrogen, oxygen, hydrogen, even neon, freezes solid long before you get this cold. Helium is special because its atoms are so light and move so quickly that they resist solidifying even at temperatures approaching absolute zero. The helium must be continuously pumped through the system, circulating through the magnets, monitored constantly and recycled. Even a tiny leak would cause catastrophic warming. If the temperature rises above the critical temperature for superconductivity, even by a few degrees, the magnets would quench. They would suddenly become resistive again. All that current flowing through them would instantly start generating heat, enormous amounts of heat. The magnets would warm rapidly, possibly damaging themselves. In 2008, exactly that happened. It was during the initial startup of the Large Hadron Collider, just 9 days after the machine had been turned on for the first time. There was excitement in the air. The media was covering the event. The machine was working beautifully. And then disaster struck. A faulty electrical connection between two magnets caused a spark. Just a small spark, a minor defect in a single connector out of thousands. But at these energies, small problems become big problems very quickly. The spark heated a small section of the machine. That heat caused the magnet to quench, to lose its superconductivity. The magnet suddenly became resistive. The enormous current flowing through it started generating heat, lots of heat, rapidly rising heat. That heat caused the liquid helium cooling the magnet to vaporize explosively. Helium is an inert gas. It doesn't react chemically with anything. But when liquid helium vaporizes, it expands by a factor of about 700. That expansion created an enormous pressure wave that ripped through the tunnel. The pressure wave damaged more than 50 magnets and ripped vacuum pipes from their mountings. Tons of helium vented into the tunnel. The tunnel pressure increased dramatically. Safety systems activated and shut everything down, preventing even more extensive damage. The repairs took 14 months. 14 months during which teams of engineers and technicians had to warm up the affected section of the tunnel, remove the damaged magnets, repair or replace them, reinstall them with modified connections to prevent the problem from recurring, test everything extensively, and then cool the system back down to operating temperature. The cost reached hundreds of millions of dollars. The delay was frustrating for physicists who had been waiting years to begin their experiments. But the incident taught valuable lessons. Every connection was inspected more carefully. Additional safety systems were installed. The machine became more robust, more reliable. The machine is fragile despite its enormous size. A bird dropping a piece of bread on an outdoor power unit once caused a shutdown. The bread attracted other animals, one of which chewed through a cable. A weasel that managed to get into an electrical substation and chewed through cables knocked the system offline for several days. Engineers have learned to expect the unexpected, to plan for failures they never imagined. But when the cold holds, when everything works as designed, something remarkable happens. The superconducting magnets lose all electrical resistance. Current flows through them without any loss of energy. In a normal wire, electricity generates heat. That heat wastes power and limits how much current you can push through. Superconductors have no such limit. The same current can circulate indefinitely without adding any energy, without any losses, without generating any heat. This is what allows the magnets to generate fields powerful enough to bend particles moving at near-light speed. The main dipole magnets in the LHC generate fields of about 8.3 Tesla, more than 100,000 times stronger than Earth's magnetic field, strong enough to levitate a frog if you put one in the field. Yes, someone actually did this experiment. A conventional electromagnet attempting to generate fields this strong would melt. It would consume enormous amounts of power just fighting its own resistance, generating heat that would quickly destroy it. A superconducting magnet simply bends space around itself, bends the paths of charged particles, does its job without complaint, without heating up, without wasting energy. There are 1,232 dipole magnets in the main ring. Each one is nearly 15 meters long and weighs 35 tons. They're massive pieces of equipment, so heavy that they had to be moved into the tunnel using specialized vehicles, so precisely engineered that they're positioned to within fractions of a millimeter. Together they contain enough niobium titanium wire to wrap around Earth's equator twice. If you unwound all the superconducting wire from all the magnets and laid it end to end, it would stretch for about 7,600 kilometers. The precision required to align these magnets is measured in fractions of a millimeter. If any magnet is even slightly misaligned, the beam will drift off course. And when the beam drifts off course at these energies, bad things happen. If any magnet fails, if any section of the ring loses its cooling and quenches, the beam loses control. Particles moving at close to light speed, carrying energies equivalent to a speeding train, would slam into the tunnel walls. They would deposit their energy in a very small area, potentially melting the metal of the vacuum chamber, definitely causing damage that would take weeks or months to repair. The machine has emergency systems designed to prevent this. Beam dump systems that can extract all the stored energy from the circulating beams and safely deposit it into a graphite absorber. Now, these systems can activate within 3 laps of the ring, less than 1,000th of a second from the detection of a problem to the safe removal of the beam. But the margin for error is razor thin. Everything must work perfectly. The cold must hold at exactly the right temperature. The magnets must fire with exactly the right strength. The beams must stay aligned to within micrometers. When they do, when everything works as designed, the collider becomes a time machine. Not a time machine in the science fiction sense, but a device that allows us to recreate conditions from the early universe, to see what matter was like when the universe was a fraction of a second old. And in 2023, this time machine was pointed at one of the strangest targets yet, something that by all rights should not exist, something that seems identical to ordinary matter in every way, yet vanished almost completely from the universe shortly after the Big Bang. The experiments at CERN were about to drop antimatter. Chapter 6. The Mirror Universe. Every particle has a twin, an opposite, an antimatter counterpart that carries reverse charges but otherwise looks identical. The electron, which carries negative electric charge, has the positron, which carries positive electric charge but is otherwise the same particle, same mass, same spin, same properties. The proton has the antiproton. The neutron has the antineutron. Even electrically neutral particles have antimatter counterparts. When matter and antimatter meet, they annihilate each other completely, converting all their mass into pure energy according to Einstein's equation E equals mc squared. This isn't theoretical. This happens. We use it in medical imaging. PET scanners work by detecting the gamma rays produced when positrons from radioactive decay annihilate with electrons in your body. The annihilation is complete, total. Both particles disappear, and what emerges is pure energy in the form of gamma rays. The conversion efficiency is 100%, far more efficient than any chemical reaction, than nuclear fission, than nuclear fusion. This is confirmed physics, measured countless times, absolutely undeniable. Antimatter exists. We can make it. We can study it. We can even store small amounts of it for short periods. But one question remained unanswered for decades. A question so fundamental that it seemed almost silly to ask, yet so important that its answer could reshape our understanding of gravity itself. Does antimatter fall up or down? It sounds strange when you first hear it. Why would antimatter behave differently in a gravitational field? Everything falls the same way, right? That's what Galileo demonstrated when he, reportedly, dropped balls from the Leaning Tower of Pisa. That's what astronauts demonstrated on the moon when they dropped a hammer and a feather and watched them hit the ground at the same time. General relativity, Einstein's theory of gravity, predicts that everything falls the same way regardless of its composition, regardless of what it's made of. A feather and a hammer dropped in a vacuum hit the ground at the same moment. Antimatter should follow the same rule. An antiproton should fall toward Earth at the same rate as a normal proton, but no one had ever tested it directly, and no one had ever actually dropped antimatter and measured which way it fell. The problem is keeping antimatter alive long enough to drop it. As soon as an antiparticle touches ordinary matter, and everything around you is ordinary matter, from the air to the floor to any container you might try to use, both the antimatter and the matter are destroyed instantly in a flash of gamma rays. You cannot hold antimatter in your hand. You cannot place it on a scale. You cannot simply let go and watch what happens. It would annihilate before you could measure anything useful. CERN built a machine specifically to solve this problem. It's called the ALPHA experiment, the Anti-Hydrogen Laser Physics Apparatus. The experiment creates antihydrogen atoms by combining antiprotons with positrons, bringing them together carefully in a vacuum chamber where they bind to form complete antimatter atoms. These antihydrogen atoms are electrically neutral, which is crucial. Neutral particles can be trapped using magnetic fields rather than electric ones, and magnetic traps don't require the antimatter to touch any physical material. The trap suspends the antihydrogen in a vacuum, in a bottle made of magnetic fields, preventing any contact with normal matter. The antihydrogen atoms hover there, floating in space, held only by carefully tuned magnetic fields. In 2023, the ALPHA team was ready to answer the question. They had refined their techniques over years of experiments. They could now create antihydrogen reliably, trap it for extended periods, and control it with precision. They created a cloud of antihydrogen atoms inside a vertical cylinder surrounded by superconducting magnetic coils. The cylinder was oriented vertically, pointing up and down. Then slowly and carefully, they weakened the magnetic trap. As the magnetic fields weakened, the anti-hydrogen atoms began to escape from the trap. Some drifted upward, some drifted downward. The atoms moved in random directions initially, but gravity, if it affected antimatter, should pull them preferentially downward. When each antimatter atom touched the cylinder wall, it annihilated. The atom and a corresponding amount of matter from the wall destroyed each other completely, releasing a flash of energy. Detectors positioned around the cylinder recorded where each flash occurred, mapping out exactly where each antihydrogen atom had travelled before it died. The team analysed thousands of these annihilation events. They measured the vertical position of each one. They accounted for the random thermal motion of the atoms. They corrected for magnetic field gradients and every other effect they could think of. The result was clear. 80% of the antimatter annihilated below the centre of the trap. Only 20% annihilated above. The conclusion was inescapable. Antimatter falls down. It responds to gravity the same way ordinary matter does. Einstein was right. Again. This might seem like the end of the story. The experiment confirmed what theory predicted. Case closed. But the implications run deeper, much deeper, into one of the greatest mysteries in all of physics. If matter and antimatter behave identically under gravity, is if they fall the same way and respond to forces the same way and have the same masses and the same properties, why is the universe made almost entirely of matter? Think about that for a moment. Look around you. Everything you see is made of matter. Your body, the air, the ground, the sun, the stars, the most distant galaxies we can observe. It's all matter. Where's all the antimatter? The Big Bang should have produced equal amounts of both. When you create particle-antiparticle pairs from pure energy, which is what happened in the early universe, you always get equal numbers. One electron and one positron. One quark and one antiquark. Perfect symmetry. They should have annihilated each other completely, leaving nothing behind but radiation. The universe should be empty except for light. No matter, no stars, no planets, no life, no you. But something broke the symmetry. Something caused matter to win by a tiny fraction, 1 part in a billion. For every billion antimatter particles created in the Big Bang, there were 1 billion and 1 matter particles. After all the annihilations, after all the matter and antimatter destroyed each other, that one extra matter particle in every billion survived. That small imbalance, 1 part in a billion, is why galaxies exist, why stars burn, why planets formed, why you're here to wonder about it. The Alpha experiment ruled out one potential explanation. Antimatter doesn't fall up. Gravity is not the reason for the imbalance. If antimatter fell upward, if it were repelled by normal matter's gravity, you could imagine a scenario where matter and antimatter segregated in the early universe, avoiding annihilation. But that's not what happens. Antimatter falls down just like matter. So what is the reason? What broke the symmetry? This is one of the most important unsolved problems in physics. We know the imbalance exists. We're living proof of it. We know it's not gravity, so it must be something else. CERN is now producing antimatter at unprecedented rates. Over 2 million antiatoms in the 2023 and 2024 runs alone. The precision of measurements keeps increasing. Each year brings new data, new tests, new opportunities to find tiny differences between matter and antimatter that might explain the imbalance. But while some scientists chased falling antimatter, others were investigating something even more puzzling. A wobble in the spin of a particle that refused to match the mathematics. For years, that wobble threatened to break physics entirely. Chapter 7. The wobbling muon. The muon is the electron's heavier cousin. It's about 200 times more massive than an electron, but otherwise similar in most respects. It carries the same negative electrical charge. It responds to the same forces. It participates in the same interactions. By all rights, it should obey the same rules. But when physicists measured how muons spin in a magnetic field, something was wrong. Something didn't match. Every charged particle with spin acts like a tiny magnet. This is quantum mechanics. Particles have intrinsic angular momentum called spin, and if they're charged, that spinning charge creates a magnetic field. Place this particle in an external magnetic field, and it wobbles like a spinning top that slowly precesses. The rate of that wobble, the precession frequency, can be calculated using quantum field theory with extraordinary precision. The calculation accounts for how the muon interacts with virtual particles that pop in and out of existence around it, how it interacts with photons and electrons and quarks and every other particle in the standard model. The calculation goes out to 10 decimal places. The measurement should match the prediction. That's how physics works. You calculate what should happen, you measure what actually happens, and if your theory is correct, the two numbers agree. In the late 1990s, an experiment at Brookhaven National Laboratory in the United States found a discrepancy. The muon wobbled slightly faster than the mathematics said it should. The difference was small, incredibly small, but it was there, persistent across many measurements. Physicists call this quantity G-2. The G represents the gyromagnetic ratio, a number that should equal exactly 2 according to basic quantum theory. Quantum field theory adds corrections that push it slightly higher, which is why we measure G-2, the deviation from the simple value. The Brookhaven results suggested the corrections were larger than expected. If true, something was interacting with the muon that the standard model didn't include. A new particle, a new force, something hidden in the quantum foam that surrounds every particle, something we hadn't discovered yet. The problem was statistics. The Brookhaven measurement was precise, but not precise enough to claim a definitive discovery. It hovered around 3 to 4 sigma, meaning there was still roughly a 1 in 1,000 chance the discrepancy was just random statistical noise, just bad luck in how the measurements happened to come out. In particle physics, the threshold for claiming a discovery is 5 sigma, less than 1 in 3.5 million chance of being wrong. Brookhaven was close, tantalizing, but not quite there. CERN contributed data from their experiments. Fermilab in the United States built a new, more precise version of the experiment. They transported the massive magnetic ring from Brookhaven across the country on a barge. It was too large and too delicate to move any other way. They shipped it down the East Coast, through the Gulf of Mexico, up the Mississippi River. It was an incredible feat of engineering just to move the equipment. Scientists spent years preparing. They improved the magnets. They developed better detectors. They refined their measurement techniques. In 2021, Fermilab released its first results. The discrepancy held. The muon still wobbled wrong, still deviated from the standard model prediction in the same direction and by roughly the same amount that Brookhaven had seen. But there was a complication. While experimentalists were improving their measurements, theorists were refining their calculations. And different calculation methods started giving different answers. Calculating the muon's wobble requires adding up contributions from every particle it could interact with, even virtually. Quarks, gluons, photons, W and Z bosons, Higgs bosons, and more exotic possibilities all contribute. Each contribution is small, but when you're aiming for 10 decimal places of precision, every contribution matters. Some of these calculations require supercomputers running for months. Others require experimental data from colliders to constrain the inputs. There are different approaches, different methodologies, different assumptions. One approach, using data from electron-positron collisions to measure how quarks contribute, supported the anomaly. The experimental muon measurement deviated from these theoretical predictions. Another approach, using a technique called lattice quantum chromodynamics, where space-time is divided into a grid and quantum field equations are solved numerically on supercomputers, suggested the standard model might be correct after all. These calculations gave a different prediction, one that was closer to the experimental measurement. The two theoretical approaches disagreed with each other, not by much, but by enough that it mattered, by enough that the existence of the anomaly depended on which calculation you believed. In June 2025, Fermilab released its final results using all 6 years of collected data. The experimental precision had reached unprecedented levels. The measurement error bars were smaller than ever before. The measurement agreed closely with the revised theoretical prediction from lattice QCD. The anomaly that had haunted physics for 25 years had faded, had shrunk to statistical insignificance. But it didn't disappear entirely. Tensions remain between different calculation methods. Different theorists still get different answers. The mystery has shifted from "is there an anomaly in the experiment?" to "which theoretical calculation is correct?" Some physicists believe new physics is still hiding in the numbers, that when all the dust settles and all the calculations are done properly, a real discrepancy will emerge. Others believe the standard model has survived another test, that there is no new physics here, just subtle theoretical calculations that are harder than anyone expected. The muon wobble cooled down as a crisis, but while that particular anomaly was fading, another crisis was heating up. A different particle had weighed in heavier than expected, and that measurement nearly shattered everything. Chapter 8: The Heavy Boson. The W boson is one of the carriers of the weak nuclear force. It's the particle that mediates certain types of radioactive decay. That allows quarks to transform into other types of quarks, that makes the sun shine by enabling the fusion reactions in its core. And its mass is one of the most precisely predicted values in all of physics. The standard model doesn't just predict that the W boson exists. It predicts exactly how much it should weigh, down to extraordinary precision. The prediction comes from measuring other particles, the Z boson, the Higgs boson, the top quark, and plugging their values into interconnected equations. Everything must balance. The equations form a web where each measurement constrains the others. If one number is off, if one mass is different than it should be, the whole structure wobbles. Something has to give. According to the standard model, after accounting for all the measurements of other particles, the W boson should weigh approximately 80,357 million electron volts, or in more standard units, about 80.357 giga-electron volts. This isn't a rough estimate. This is a precise prediction with small error bars. A prediction that comes from decades of measurements at particle colliders around the world. In April 2022, the CDF experiment at Fermilab dropped a bomb on the physics community. CDF, the collider detector at Fermilab, had been collecting data for decades, throughout the 1990s and 2000s. Even though the Tevatron collider had shut down in 2011, the team continued analysing their data, squeezing out every last bit of information. After analysing data collected over more than 2 decades of operation, they announced a new measurement of the W boson mass. Their value was 80,433 million electron volts, 80.433 giga-electron volts. That's 76 million electron volts higher than the standard model prediction. That's 0.1% heavier than it should be. Now, 0.1% might not sound like much, but in particle physics, where we routinely measure things to parts per million or better, 0.1% is enormous. The discrepancy was 7 sigma. 7 sigma. Remember that 5 sigma is the threshold for claiming a discovery, corresponding to a less than 1 in 3.5 million chance of being wrong. 7 sigma means the chance of this being a statistical fluke, just random bad luck in how the measurements happen to come out, is less than 1 in a trillion. Less than 1 in 1 trillion. If this measurement was correct, the standard model was broken. Fundamentally, deeply broken. Physicists around the world scrambled to understand what it could mean. Some proposed new particles that had escaped detection, particles that would contribute to the W boson mass through quantum loops. Others suggested the Higgs boson might interact with undiscovered forces in ways we hadn't anticipated. A few speculated about extra dimensions or supersymmetric partners hiding just beyond our ability to detect them directly. The measurement, if correct, would be the first definitive evidence for physics beyond the standard model. It would be the crack in the edifice we'd been searching for, the thread that when pulled would unravel our entire understanding of particle physics and lead us to a deeper, more complete theory. But there was a problem. A big problem. Other experiments didn't agree. Measurements from ATLAS and CMS at CERN, using data from the Large Hadron Collider, gave values closer to the standard model prediction. Earlier measurements from LEP, the electron-positron collider that operated at CERN before the LHC, also agreed with the standard model. Even earlier measurements from the Tevatron itself, from a different detector, gave different results than CDF. The CDF results stood alone. One experiment saying something dramatically different than all the others. Either CDF had discovered something revolutionary, something that all the other experiments had somehow missed or measured incorrectly, or they had made an error somewhere in their analysis. Measuring the W boson mass is extraordinarily difficult. The W boson is unstable. It decays almost immediately after being produced. One of its common decay modes is to a muon and a neutrino. Muons can be tracked precisely by detectors. We can measure their energy and momentum accurately. But neutrinos are a problem. Neutrinos barely interact with anything. They escape the detector without triggering any sensors, without leaving any trace. You cannot measure a neutrino directly in a detector like this. You can only infer its properties from what's missing in the collision. You add up the energy and momentum of all the particles you can see, and whatever's missing, whatever's needed to make the books balance, that must have been carried away by the neutrino. This requires perfect understanding of the detector. Every magnetic field must be mapped precisely. Every material interaction must be modeled accurately. Every calibration must be known exactly. Small systematic errors, errors that don't average out over many measurements, can shift the final result. For 2 years, the physics community waited. Theorists wrote hundreds of papers proposing explanations for the discrepancy. Experimentalists examined their own data more carefully, looking for similar effects. Then, in September 2024, the CMS experiment at CERN released its own measurement of the W boson mass. They used 300 million collision events collected between 2016 and 2018. They developed new analysis techniques specifically designed to minimize systematic uncertainties. They spent years checking and rechecking their work. Their result, 80,360 million electron volts. Almost exactly what the standard model predicted. The error bars were small. They were confident in their measurement. The CDF anomaly did not replicate. The crisis appeared to be over. But mysteries remain. Why did CDF get such a different answer? Their analysis methods have been examined extensively by other physicists, and no obvious errors have been identified. The CDF team stands by their measurement. Some physicists believe there are undiscovered systematic effects, subtle biases in the detector response or the analysis procedure that shifted the result. Others wonder if there's something deeper, if the disagreement hints at something we don't understand yet. For now, the standard model has survived. The W boson weighs what it should. The equations still balance. But just because one crack sealed doesn't mean others haven't opened. In the debris of collisions, scientists have found particles that should not exist at all. Chapter 9. The exotic particles. Quarks are the building blocks inside protons and neutrons, the fundamental constituents of the atomic nucleus, the particles that make up the matter in your body and in every star and planet. They come in 6 types, which physicists call flavors, for no particularly good reason other than we needed names for them. Up and down are the lightest, the quarks that make up ordinary protons and neutrons. Then come charm and strange, heavier versions. And finally, top and bottom, the heaviest quarks, existing only briefly in high-energy collisions or cosmic ray impacts. Normally, quarks combine in simple patterns. 3 quarks make a baryon, like the proton, up, up, down, or neutron, up, down, down in your body. 2 quarks, specifically 1 quark and 1 antiquark, make a meson, a type of particle that mediates the strong force inside atomic nuclei. For decades, these were the only combinations observed, baryons and mesons, 3 quarks or 2 quarks. That's it. That's all we ever saw. But the theory allowed more. The mathematical framework of quantum chromodynamics, our theory of the strong force, permitted other combinations. 4 quarks bound together, 5 quarks locked in a single particle, 6 or more. These exotic states were predicted in the 1960s, at the same time the quark model was invented. Murray-Gell-Mann, who proposed the quark model, even speculated about their existence. But no one could find them. Experiment after experiment, collider after collider, search after search, nothing. Some physicists began to doubt they existed at all. Maybe the mathematical possibility didn't correspond to physical reality. Maybe the strong force just didn't work that way. Then the Large Hadron Collider started smashing particles together, and everything changed. The LHCb detector, LHC Beauty, specializes in studying bottom quarks and charm quarks. These heavy quarks are produced copiously in high-energy collisions. They're also unstable, living just long enough to travel a fraction of a millimeter before decaying into lighter particles. That tiny travel distance is measurable. The silicon detectors at LHCb can track particles with micrometer precision, and a bottom quark traveling a fraction of a millimeter leaves a visible track, a slight displacement between where it was created and where it decayed. By analyzing those displaced tracks, physicists began finding things that didn't match any known particle. Combinations of particles appearing together that couldn't be explained by known processes. Masses and decay patterns that suggested something new. In 2015, LHCb announced the first confirmed pentaquark, 5 quarks bound together in a single particle. The particle contained a charm quark, a charm antiquark, an up quark, a down quark, and another quark. It existed for only a tiny fraction of a second before falling apart, but the signal was unmistakable. The statistics were solid. This was real. Then came the tetraquarks, 4 quark particles. In 2020, the collaboration found a particle made of 4 charm quarks, 2 charm quarks and 2 charm antiquarks, all bound together in a tight cluster. This was extraordinary. All previous tetraquarks had contained a mix of heavy and light quarks, maybe 1 heavy quark and 3 light ones. This was purely heavy, 4 charm quarks, all heavy, all bound together somehow. The discovery changed how physicists think about the strong force. It showed that quarks could bind in ways we hadn't anticipated, in configurations that seemed impossibly unlikely but were nevertheless real. In 2022, the announcements accelerated. 3 new exotic particles in a single report. A pentaquark containing a strange quark, the first of its kind. A pair of tetraquarks, one with double electric charge and one neutral, appearing together in the same decay process. The statistical significance was overwhelming. 15 sigma for the pentaquark, 6 sigma for the tetraquarks. These were not random noise. These were not statistical flukes. These were real objects, real particles that existed and could be studied. But what exactly are they? This is where things get interesting. 2 models compete to explain these exotic particles. In one model, the quarks bind tightly together into a single compact object, a true 5-quark or 4-quark particle where all the quarks are at about the same location, held together by the strong force in a new kind of configuration. In the other model, the particle is more like a molecule. 2 ordinary hadrons, like 2 mesons or a baryon and a meson, held loosely near each other by the residual strong force, not fully merged into a single object, but not quite separate either. Like how atoms bind into molecules without their electrons truly mixing together. The answer matters. Understanding how quarks bind at this level helps us understand the strong force itself, one of the 4 fundamental forces of nature, the force that holds atomic nuclei together, the force that makes nuclear bombs work and stars shine. It also helps physicists calculate what should happen in extreme environments, like the cores of neutron stars, where matter is compressed to densities higher than atomic nuclei, or in the first moments after the Big Bang, when the universe was so hot and dense that quarks couldn't form normal protons and neutrons. More than 60 new hadrons have been discovered at the LHC so far. Most are exotic states that had never been observed before. The particle zoo is growing larger and stranger than anyone anticipated. And among those new arrivals, scientists found something that connected quantum mechanics to energies never before tested. 2 particles entangled across space-time, behaving as one. Chapter 10. Quantum entanglement at the extremes. Quantum entanglement is one of the strangest phenomena in all of physics. When 2 particles become entangled, their properties are linked. Measure one particle and you instantly know something about the other, no matter how far apart they are. Einstein called it spooky action at a distance. He didn't like it. He thought it suggested quantum mechanics was incomplete, that there must be some hidden variable, some deeper theory that would explain this apparent non-locality without requiring instant correlations across vast distances. He was wrong. Quantum entanglement is real. Experiments have confirmed it countless times over the decades, using photons and electrons and atoms. The particles genuinely behave as a single system, even when separated by kilometers. The 2022 Nobel Prize in Physics was awarded specifically for experiments that proved entanglement is genuine and that Einstein's hoped-for hidden variables cannot explain it. However, all these previous experiments occurred at low energies, tabletop setups, lasers and crystals and cold atoms. The quantum effects were gentle, contained, safe. You could do these experiments in a university laboratory with modest equipment. No one had observed entanglement at the violent energies inside a particle collider, where particles collide at speeds approaching light speed, where temperatures exceed those in stellar cores, where the quantum fields themselves are pushed to their breaking points, until 2023. The Atlas collaboration at CERN announced they had detected quantum entanglement between top quarks. These are the heaviest fundamental particles known to exist. Each one weighs about as much as an entire gold atom, roughly 173 billion electron volts. They're so heavy that they're produced only in the most extreme collisions, and they're so unstable that they decay in less than 10 to the power of minus 25 seconds, a trillionth of a second. There's literally no time for top quarks to interact with other particles or to exchange information with each other. They're created and they decay, faster than light could cross the distance between them. Their quantum properties must be measured through the debris they leave behind, through the particles they decay into. The experiment focused on pairs of top quarks produced when two protons collided head-on. By measuring the angles between the decay products, the angles at which the daughter particles flew apart, physicists could infer the spin states of the original top quarks. If the spins were correlated in a specific way, a way that violated classical physics but matched quantum mechanics predictions, it would prove the top quarks were entangled. The result exceeded 5 sigma. Entanglement was confirmed at energies roughly 1 trillion times higher than previous entanglement experiments. The particles were created in conditions that existed only a trillionth of a second after the Big Bang. The CMS collaboration replicated the finding with their own independent data. They went even further, examining pairs of quarks moving at high relative speeds where classical communication between the particles would be impossible even at light speed. The particles were moving apart so fast that light wouldn't have time to cross between them. Entanglement still held. The quantum correlations persisted even under these extreme conditions. This matters for more than just confirming quantum mechanics, which by this point has been tested so thoroughly that few physicists doubted it would work at these energies. What matters is that the techniques used to detect entanglement at the LHC can now be applied to search for new physics. Any deviation from the predicted spin correlations would indicate unknown particles or forces interfering with the system. If some new particle was being created in the collisions and affecting the top quarks, it would show up as anomalies in the entanglement pattern. So far, no deviations have been found. The standard model continues to describe reality at the highest energies we can test. Quantum mechanics remains unbroken, working exactly as the mathematics says it should, even in the most violent environment humans can create. But confirming the old theories was never the main goal. CERN exists to find what lies beyond, to discover what our current theories can't explain. And in the subtle differences between matter and antimatter, scientists found a clue that might explain why the universe exists at all.